Okay, so it's my great pleasure to introduce Professor Pearl Sandick as our colloquium speaker. I've known Pearl for quite some time, and in fact, I was struggling to figure out exactly how many years I've known Pearl for. We've worked together on a lot of things to do with women in physics and a lot of four corners issues. Pearl has been on the Committee on the Status of Women in Physics. More recently, she's been chair of the Four Corners section, and she has also chaired the National Organizing Committee of QWIP, which I know many of my students went to and enjoyed. She earned her PhD from Minnesota. She was a postdoc at UT Austin, and she moved to Utah in 2011. She's now a professor in the Department of Physics and Astronomy, an associate dean for faculty and research in the College of Science at the University of Utah. She is actually a great communicator of science and a great advocate for science and scientists. Her research is focused on physics beyond the standard model, which is the topic of this colloquium. So let's welcome her to Arizona State.
All right, thank you. Let me get this set up here. Can you hear me? Is that good? Okay, great. Okay, so now that Tricia has set the bar quite high for my talk, I'm going to talk about highs and lows in the search for dark matter. So my goal here is to cover kind of a lot of ground, but I want to give you a flavor for how exciting this field is and how many different things are going on. So I'll start with sort of the basic overview. What is the universe made of? If we think about all of the matter in the universe, the vast majority of it is made of stuff that we do not understand, dark matter, right? So we know the heavy elements, we know that there are neutrinos, which in some ways behave as dark matter. We know that a lot of it is stars, but most of it is free hydrogen and helium. And then there's this vast component of the matter density of the universe that gravitates, but we actually really don't know very much else about it. We know some things that it's not, but we don't know what it is, and we haven't observed it to interact any other way. I always start out by talking about the gravitational evidence because basically everything we know about dark matter, the things that we do know, are purely from gravitational evidence. And this is the picture that I show, no matter whether I'm talking to like my daughter's friends at school or a bunch of PhD physicists, because it's really important that we understand exactly like what's going on here, right? And it's also important that we're able to talk about this with other people. So all of our gravitational evidence in some way is related to Newton's second law. And basically the idea here is just that if you know the rotational velocity, like let's say you're looking at this galaxy and there's a star orbiting the galaxy, if you know the rotational velocity of that test mass, then you can compute the force. And we know how to do that, right? It's the mass of the object that's in rotation, little m, times the mass contained within its orbit at a radius r, times Newton's constant g divided by r squared. And this is, if this is circular rotation, then we can relate that to the rotational velocity squared. When you're explaining this to other people, they may not be so familiar, though, with looking up at a galaxy and watching objects rotate around in a galaxy. And so I actually like to show this picture, which everyone can relate to, right? How many of you have played with something like this? Yeah, okay, you know what it means, right? If you want that thing to go faster, it's going to pull on your ankle harder, right? That's the whole idea here. And so if we know the rotational velocity, then we can relate that to the amount of force that's pulling on it or the mass contained within a radius r. This is the principle, right? Now, of course, we know who did this. This was Vera Rubin, who used this method, which was really, it wasn't the first piece of evidence for dark matter necessarily, but it was the one that made people really pay attention. So Vera Rubin did this with galactic rotation curves in the 60s and 70s and made some really groundbreaking advances in that allowed us to have these really excellent measurements that people trusted of galactic rotation curves. And the idea was that, okay, so that it should be proportional to the square root of the mass contained within the radius r divided by r. But as you go far outside of the mass distribution, if the mass contained within a radius r is pretty much constant, then you would expect it to fall off like 1 over the square root of r. But of course, that's not what was observed, right? So what was observed, you're looking at the rotational velocity. Do I have a pointer? Maybe I do have a pointer. Okay. So you're looking at the rotational velocity as a function of radius. And you can see that first it increases as you would expect. And there are two components listed here. There's the gas in this galaxy and what you would expect from the disk. This is the rotational velocity that you would expect from those two components. But what was measured is like vastly different than both of those two things, right? So how do you explain that? And the way that you explain it, the way that some people explain it, is by adding an extra halo component. So something that gravitates, that has some sort of distribution that explains the difference between the expected contributions from regular matter and what's observed. Okay, now you can visualize this, and people have done this, like it's really cool to actually look at it happen. So on the left here, you have a picture of a simulation of a galaxy without dark matter, and you can see below that, that's the rotation curve that you would expect from that scenario, and with dark matter. So we know what these look like, but you can actually see it just by eye, which is kind of cool too, right? So if you look at the left picture, especially if you look at the things that are sort of around the outer edge of the galaxy, they're moving pretty slowly, whereas in the right picture, they're moving fast. There's like a visible difference. Like we know this stuff is there. So that's one type of evidence, right? All of our evidence is sort of gravitational in nature in some way. We have a lot of different types of observations now, right? So we certainly have galactic rotation curves. We have sort of similar types of measurements of clusters, including collisions of clusters that we know happen, most famously the bullet cluster, which is kind of in the middle here. Weak gravitational lensing tells us about the distribution of dark matter. Of course, that contributes to this bullet cluster picture. We know that structure formation, in order for structures to form and clump together, there had to be something extra that helps things bind together. So we need an additional gravitational component. And all of this fits into this concordance picture, the concordance model of cosmology, where we have some dark energy that's kind of helping things move apart and some dark matter that's helping things bind together. So we know that some explanation is necessary for these phenomena that we're observing. Pretty much everywhere we look, there's extra dark matter that we can't explain with regular matter. We know how much of it there is. There's a lot. We know the energy density of the universe. Whatever it is that is an explanation for the dark matter has to be cold in order to bind things together. So we use the word cold to mean non-relativistic. We also know that it was around in the early universe and it's still there today. So it has to be stable on the time scale of the universe. It's dark, which means that it doesn't interact with photons that much. It's largely neutral to the extent that we couldn't have seen it yet. And it's not regular matter. And we know this for a bunch of reasons: structure formation, abundances of heavy elements. There's all kinds of things that would get messed up if it were some part of regular matter, unless it was all bound up in black holes. So what could it be? It could be possible for me to ask you all, what do you think dark matter is, and get a different answer from every person. That is actually totally possible, right? There are tons of explanations for dark matter, and I know there are people in this room that study various different types of explanations for dark matter. I'm going to focus on one today, but that is by no means means this is the only explanation for dark matter. But it's a very popular one, and I like to use this as an example because it kind of threads its way through all these different detection strategies that I'm going to talk about. So the candidate that I'm going to talk about is called a WIMP. And the key feature of WIMP dark matter is that its abundance, how much there is in the universe today, is obtained through a particular process called thermal freeze-out. So imagine we're in the very early universe. Things are very hot and very dense. And every time you have like two new dark matter particles, let's say that are a little bit heavy, every time they have an interaction, they can annihilate and produce standard model particles, regular matter particles. And whenever you get, like, let's say an electron and a positron, they could potentially annihilate and produce two dark matter particles. So in the universe, hot and dense, both of these things are happening a lot, and there's some number density of dark matter that you would expect. So what you're looking at here is a plot of the co-moving number density. So we say co-moving to factor out the expansion of the universe, so we don't have to worry about that. So this is the number density of dark matter as a function of this parameter, which is mass divided by time, or mass divided by temperature. So time is increasing to the right. So in the early universe, there's some equilibrium situation. However, the universe is expanding and cooling, right? So the first thing that happens is that the universe cools to the point where if these dark matter particles are heavier than regular matter particles, they don't have enough energy when they meet each other to produce two standard model particles don't have enough energy when they meet each other to produce a heavier dark matter particle. So at that point, you start losing this direction of the process. You can't produce new dark matter particles, you're just losing them, right? Okay, so the number density drops. Eventually, the expansion of the universe actually becomes important for this process, and it becomes hard for dark matter particles to find each other to annihilate in any like meaningful quantity. And so however many particles, or however many dark matter particles you have at that time, you're kind of stuck with, more or less. And so that tells you how many are left over today. It was when they froze out from this thermal expansion. And it turns out that you can do this calculation with the Boltzmann equation. And what you find is that if you have these new dark matter particles that are roughly stable, that have masses in the GeV to TeV range, a GeV is like the mass of a proton, basically, right? So if you have stable matter with masses in that range and annihilation cross-section that's typical of like the weak interaction, what you find is basically the right amount of dark matter left over in the universe today, which is pretty like, that's pretty remarkable, because those are all parameters that we kind of understand from particle physics. So this seems to be telling you that a good candidate is something that we would call weakly interacting and massive, and therefore a WIMP. What I find remarkable about this picture is that this seems to be telling us that, like, cosmology seems to be telling us that we need new particles at the GeV to TeV scale. This can't be regular matter. And one of the reasons that I find that so cool is because I grew up in like the particle physics side of things rather than the astrophysics or cosmology side of things. And I grew up thinking about the standard model and being taught all these reasons why we need new physics beyond the standard model. And this is another one that's coming from some completely separate concern. So here's the standard model. Many of you have probably seen this picture before. We have 6 quarks. We have charged and neutral leptons, gauge bosons, Higgs boson. The standard model works. It's been verified by collider experiments. Almost every collider study that's been done tells you that the standard model basically works. Anomaly here and there maybe, but we usually figure out what those are. However, for theoretical reasons, we know that it's not complete. So I already mentioned that it doesn't include dark matter. It also doesn't include any explanation for dark energy. But maybe even more troubling, we know that neutrinos have mass, and there is no way to accommodate that within the standard model of particle physics. You need something new. It doesn't include gravity. It also can't be accommodated within the standard model. It can't explain why the universe ended up with this amount of matter relative to antimatter. That was from a matter-antimatter asymmetry in the very early universe. And you can calculate what matter-antimatter asymmetry you would expect within the standard model, if that's all that there is, and it's way wrong. So it means that there's something we're missing, right? There's this question of the hierarchy problem, like why do the forces have such different strengths? In particular, why is gravity so weak? And there are other reasons too. And many of these puzzles could or should be addressed within a theory that has new physics at the TeV or GeV scale. So from the particle physics side and from the cosmology side, we seem to be arriving at this like need for new physics beyond the standard model at this particular mass scale. So if dark matter is a particle with a weak scale mass and cross section, there are a bunch of different ways we can find it. And in fact, this is true more generically as well. We don't know how dark matter interacts with the standard model. We hope that it does. So let's presume that it does, and then see how we can figure out what it is. So this is like a mock-up of a Feynman diagram. If we knew what the theory of new physics is, then we could say what the dark matter is and how it's connected to the standard model, right? We could draw in those lines. But in the absence of that, we'll just put a circle there. We're not sure. So if you read this diagram from left to right, 2 dark matter particles find each other. If there's enough dark matter around, that can happen. They annihilate and produce standard model particles. Looking for those standard model particles is a strategy that we call indirect detection. And they could be coming from sort of anywhere in our galaxy or beyond our galaxy. If you read it from right to left, so 2 standard model particles, if you give them enough energy and smash them into each other, you could end up with a collision that creates 2 dark matter particles. And that's a strategy that people are trying to pursue at colliders. And then you can read it from top to bottom or bottom to top. So if you have a standard model particle sitting there and a dark matter particle bumps into it, which should happen, maybe, you should be able to maybe observe a recoil of a standard model particle. And so that's a strategy that we call direct detection. And there's one more thing that it's kind of hard to even see how it would fit into this diagram, but any astrophysical signature that tells us something about the non-gravitational nature of dark matter, we call astrophysical probes. So that might be if dark matter interacts with itself, and that changes like the shape of the distribution in a galaxy, for example. And if we can observe that, then that would be an astrophysical probe of the non-gravitational nature of dark matter. Okay, so I'm going to start with collider searches, and I'm just going to go through these very briefly and tell you about some things that I think are exciting at the end. So collider searches are maybe the most straightforward thing. If you want to discover a new particle, the best thing to do is just produce it in a lab, right? Like that's a controlled environment. That would be cool. And I remember back when I was a graduate student and everyone was very optimistic about just directly producing dark matter and then measuring it at a particle collider. And that would be really good, except that if you produce dark matter, it very rarely interacts with other stuff. Otherwise, we would have seen it. And so the most likely thing it's going to do is just fly out of your detector. So you might find it, you might be looking for missing energy, right? And it turns out that's actually a really hard thing to do. So what's a little bit easier is if you look for let's say what happens to the LHC often is that you have a quark and an anti-quark that are actually having an interaction. Those are the two things that have the relevant interaction. And you can produce two dark matter particles, but you can also radiate something from the initial state. And so if the dark matter flies out of your detector, that's missing energy. But what you might get left over with is one extra thing, whether that's a gluon or a photon or a Z boson or something like that. So we call those mono something searches. And that's a pretty common search strategy. If your dark matter exists within a bigger theory, like maybe one extra particle for dark matter is not the answer. Maybe it exists within a theory that predicts lots of new particles, like supersymmetry, for example, then observing those particles at a collider is also a really important strategy. Okay. I can't tell if this is, there we go. Okay, might have missed something there, but that's all right. So collider searches are fantastic for a lot of reasons. The upside is that this is completely independent of astrophysics. This is the equivalent of your tabletop experiment that you could try to do to produce dark matter. And you can measure, potentially, you can measure the mass and the couplings of any new particles that you produce, which would tell you more about your theory that hopefully includes dark matter. However, if you produce a new particle at a collider and it flies out of your detector and that's the signature, you will not be able to determine whether the thing you produced is actually stable on cosmological scales, which it would have to be in order for it to explain the dark matter. So you're going to need some other kind of astrophysical measurement in order to verify that, right? So what's next, what's currently happening, I should say, is that the LHC is in what's called run 3. The LHC has been operating for a number of years now. It's currently operating at 14 TeV. I put some references in here because I've kind of worked on a lot of these things in various ways. But the LHC is still a really important detection strategy. We are looking forward to maybe future colliders. There's another important aspect of this, which is investment in precision physics. And the muon G-2 experiment is one example of that. But if there is any new physics beyond the standard model, even apart from dark matter, then hopefully it'll show up if we make really, really good measurements of processes that we know are happening. I wanted to show you the run schedule for the LHC so you can kind of get a feeling for this. So this is sort of, you can see that you are here at the beginning of 2024, and we're like in the middle of run 3 at the LHC. Pretty soon, at the end of 2025, there's going to be a long shutdown. This will be the third long shutdown, and that's a time for detector upgrades. When it comes back online, it's going to come back as the high luminosity LHC. Energy is not going to be higher, but we'll have 4 times more collisions for each per unit time, basically. So right now, every time there is a collision point, a beam crossing, you get about 30 collisions out of that. And it's already hard to figure out what's happening with 30 collisions that are happening at the same time, right? And then you have to look at that snapshot, record it somehow if there's anything interesting in there, and try to decipher what's going on. When it comes back as high luminosity LHC, there are going to be about 130 collisions for every beam crossing, which is a lot, right? So that's a big challenge. But hopefully it'll tell us a lot more because we'll just be able to get data faster. Okay, let's switch gears a little bit and talk about direct detection. So the idea of direct detection is these dark matter particles are all around us, right? We definitely know that. They're probably flying through us right now. And as they do that, occasionally they're going to bump into nuclei. There's going to be a measurable, hopefully measurable collision with the nucleus. If you're going to build an experiment to detect that, you want to be able to estimate how often that happens. So here's how you would estimate that. This is a differential recoil rate. So what goes into that? First, you need the flux of dark matter particles, the flux of WIMPs. So that depends on the local density of WIMPs, rho naught, the speed at which they're moving, v, and the mass of the dark matter particles, m chi. They're probably not all moving at the same speed, right? Most things have some distribution of velocities, and so you have to account for the velocity distribution. And then there's the piece that really is the particle physics part. Like this is what I calculate as the probability of my dark matter particle interacting with the target nucleus, which depends on the properties of the dark matter model. You integrate that over velocities that are going to produce recoils that are energetic enough to measure, right? So there's some threshold energy, and you get this differential rate. And to give you an idea of how rare this is, the units that are used to describe this thing are the number of counts per ton of detector material per year per KeV. So, and the numbers are like 1, right? So this is an extremely rare thing that you're looking for. You have to build a big detector, and you have to really understand any backgrounds in there and try to eliminate as many backgrounds as you can. There are other things flying through us that could do this to nuclei, right? Like cosmic rays and radioactive material that's near your detector. And so in order to understand that or have confidence that what you're observing is a dark matter particle bumping into a nucleus, you have to get rid of all those other things. So you go deep, deep underground in order to avoid all of these backgrounds, right? So where are we in direct detection? So this is a picture of on the y-axis, you have the cross section in square centimeters. So that's the sort of the probability that you're going to have, that your dark matter particle is going to interact with a nucleus for different WIMP masses. And all of these are, pretty much all of these are exclusion curves. So you can imagine that roughly everything in the green area, the cross sections are so big, the probability of interacting with the target nucleus is so big that we would have seen it if it were there. We haven't seen it. So now we march down in this plane. There have been some really interesting hints over the last decade. I will tell you about one first that very clearly worked out to not be what we thought it was. This was in about June of 2020, I guess June of 2020. Xenon 1 ton, which is a giant vat of xenon underneath a mountain in Italy, said that they had an excess of KeV electron recoil events. And that's a thing that dark matter could create. And in fact, we proposed a particular type of dark matter that could create that type of signal, which is called boosted dark matter. Regular WIMPs wouldn't do it, so you needed something a little bit special. And what you're seeing on the right is a picture. This is the black dots are the data, and you can see there's a big bump right here. And the red curve is what our model predicted, which is like very exciting. We're like, oh, this could be the thing, right? And then we proposed follow-up studies because there would be a really interesting like diurnal modulation of this thing. And Xenon 1 ton then went back, they looked at their data more carefully, and they said, actually, you know what it is? It's probably tritium decays, and so never mind. That said, boosted dark matter is still interesting. It's just not the explanation for this particular thing. That one was very short-lived, but there's another sort of anomaly in direct detection that has been around for a really long time, which is from the DAMA experiment. I want to just say a couple words about that. So the DAMA experiment is looking for something that most other dark matter experiments are not looking for. It's looking for an annual modulation of the dark matter signal. So if you imagine the dark matter is all around us, right? It's basically clustered around the galaxy. So it's in the galaxy's rest frame, more or less. But we and our experiments are in the solar system, and in particular on Earth, these direct detection experiments. So, the solar system is moving around the galaxy, right? And at some times of the year, the motion of the Earth is with the motion of the solar system around the galaxy, like in June, and at other times it's against the motion of the Earth. So what the experiments on Earth would see is that sometimes you're flying faster into this dark matter wind, and sometimes you're flying slower into the dark matter wind. So because of this, they were looking for a variation throughout the year of events due to dark matter scatterings. And this experiment has been going on for more than, well, decades now. And at the beginning, you can see this is sort of their early data. Oh yeah, it kind of looks like a modulation. The curve is really there to guide the eye. And then they upgraded and they came back as DAMA Libra and with a slightly better sensitivity. And you can see there's a very clear modulation. And then they kept going, and now they don't even plot all the data on one picture anymore. But I don't think anybody disputes that there is some sort of modulation that's being seen here. So can we investigate that? How can we know? Are they actually seeing dark matter? Well, I'm going to go back just for a moment to this picture. The regions that you would expect, the dark matter models that would produce such a signal, are actually way up here in this excluded green desert. So it's a little bit curious. And there have been a lot of different explanations for what it possibly could be. None has been verified. So we looked at I had it here. So we looked at very briefly one thing that possibly could be. The DAMA uses sodium iodide crystals, but there might be something else in there. In particular, there might be some dopants, and we looked at thallium as a possible dopant, which would have a different scattering cross-section than sodium and iodide for dark matter. And so we said, what if there's a certain amount of thallium in there? Could that possibly explain it? And it turns out that it can't, although that had been an explanation that people put forward for several years. So we don't know. There is no resolution, but there is hope because there is an experiment called Anais that is using the same sodium iodide crystals, and it's looking for the modulation. So far, they don't see it. So I think it's excluded at 3 sigma now. And by 2025, they expect to have a sort of 5 sigma result that there is no modulation. All right, so what's next? I talked about resolving this domain modulation question, which is really important. I also want to say, like, these constraints are going down and down and down to lower and lower cross sections, tinier and tinier probabilities of interactions between the dark matter particles and the nuclei. These are all still in the range of things that we would expect from sort of typical dark matter models, but the cross sections are getting smaller. And there's another thing that's flying through us all the time that interacts with nuclei in a very similar way, and those are neutrinos. And so eventually what these dark matter experiments are going to be looking at when their sensitivity is, when they're sensitive enough, they're going to actually be seeing neutrino scatterings in their detectors. So neutrino coherent scattering was measured several years ago now for the first time directly, and that's what these dark matter experiments are going to be looking for. So in some sense, they'll become neutrino detectors, but in another sense, that's sort of just like a background to detecting dark matter, and that's something that there are ways to work around. Another interesting direction is the parameter space, the dark matter masses like GeV plus that have been typically probed or typically targeted by these direct detection experiments. It's almost like because the lamppost was there, that's why we're looking at it, because these elements and these detector materials lead to interactions that are measurable with that mass. However, lighter dark matter is also really interesting. So there's a movement towards sub-GeV dark matter. And the last thing is, most of the dark matter detection experiments that exist today don't care what direction the dark matter comes from. Like, they just measure a scattering in the detector or no scattering in the detector. And directional dark matter searches, even if they're just bidirectional, can really tell a lot of the story in terms of what is the origin of those scattering events. There's one caveat. So similar to the caveat for collider searches, you needed a secondary technique, and here you do too. And the reason is because if you look at this recoil energy calculation, you can see that it's sensitive to the product of the local density of dark matter, rho, times the scattering cross-section, sigma. And so it could be that you have something that only makes up part of the dark matter, a small rho, right? Not the whole dark matter rho, but has a larger cross section. You can't untangle that. They're intrinsically linked here. Okay, so I'm going to move on to indirect detection. Indirect detection, the idea here, of course, is to look for the end products of dark matter annihilation. So this is sort of one cartoon picture, right? 2 dark matter particles annihilate and produce regular matter stuff that hopefully we can observe. If dark matter annihilated in the early universe, I show you that thermal freeze-out picture. If it did that in the early universe, it's probably still doing it somehow today. So that makes this detection technique really compelling. And it's one of the few ways that we can really directly link that early universe physics and physics that could be happening today. Now, there are a bunch of challenges, right? What you're looking at here, maybe I'll say that first. What you're looking at here is the gamma ray sky as measured by the Fermi Gamma Ray Telescope. And you can see that there's a whole lot of structure. There's a lot of stuff going on there, right? So just to, I'm going to go with the third bullet point first. It is often very difficult to exclude astrophysical explanations, and I'll say how that comes into play in one particular place in just a minute. The dark matter indirect detection is always sensitive to the distribution of dark matter between you and the target, and then behind the target too, right? All you're seeing is the stuff in that direction when you're looking at using your telescope to look in that direction. And if you're looking especially for charged annihilation products, then they're going to propagate. There are magnetic fields. There are dust that can prevent you from seeing the signal, or that can interfere with the signal. So it's not a straightforward thing to do, but there are a lot of targets that you can look at, and they each come with pros and cons. Now, I've been talking about WIMP annihilation, and I've been showing you that cartoony picture, but I want to just say a little bit more about what that actually means. So if you look at the top, if you look at the bottom picture, so this looks a lot like what I've been showing you, right? 2 dark matter particles on the left side, they do something, somehow interact with each other, and in the final state, maybe you have 2 photons. That would be really easy and a really clean signature if we could see that. But if dark matter interacted that easily with photons, we probably would have seen it by now. So in most models, this is suppressed for various reasons, and it's also suppressed because we don't see it. What is probably happening is something more like the top picture, where you have two dark matter particles, they interact with each other somehow and produce pairs of standard model particles, or two standard model particles, or maybe three standard model particles, not sure. But often the things that will be produced here will be things like a quark-antiquark pair. And we all know that if you produce a quark and an antiquark, they're not just going to sit there. They're going to hadronize and stuff is going to decay, and you get a big mess of stuff at the end of stable products. So it's the stable products that you can look for. So that would be things like gamma rays or photons of other energy ranges, neutrinos, some antimatter, even composite objects that are matter and antimatter. So those are the kinds of things that we're looking at with various different types of telescopes. So just as we did for direct detection, let's sort of think about how we would calculate an expected signal, right? So you can calculate the flux of dark matter, of products of dark matter annihilation, roughly in this way. So if we have photons as our example, obviously this depends on the dark matter mass. That's just sort of scaling how many of them you have. If they're very massive, you need fewer dark matter particles to make up the dark matter in the universe that we observe gravitationally. They may not all annihilate to the same thing all the time, right? Often it goes to W plus W minus sometimes and quarks other times. So there's some branching fraction to different final states, and you sum up over the different final states. And each of those different final states has a different type of photon spectrum from decays and hadronizations. And then you need to integrate that. You integrate the annihilation cross-section, so the efficiency of this annihilation process happening, which depends on and multiplied by the distribution, the density of dark matter squared. Okay, so if you have more dark matter, you're going to get more annihilation. That squares. So in practice, you're going to measure the flux of photons. That's what experiments do. They measure the photon flux. And then you make a whole bunch of assumptions about what your dark matter model is. And typically what we do is we use that to put a limit on the annihilation cross-section, or it's often expressed annihilation cross-section times V. And the reason is because that quantity in many models itself is velocity independent. So where do we look for these things? I mentioned that there are a lot of different places to look. We could look at all of the dark matter annihilations that might be happening in the whole halo, right? So look at all the photons from the whole halo, or all the neutrinos from the whole halo. We could look sort of in a more pointed observation towards the galactic center. We can look for annihilations that might be happening actually if dark matter has collected in the sun or the Earth. That gives us a very crisp and clear target. One target that gets a lot of attention these days is nearby dwarf galaxies. These things are dark matter dense and nearby us. They make really good targets. Or in Milky Way substructure is another option. So first I want to say a little bit about the Milky Way galactic center, because that's a place where there's some other interesting stuff going on. So for many years now, more than a decade, I believe, this is not the first paper that pointed this out, there has been an excess of GeV photons coming from the galactic center region. Now I showed you that picture of the Fermi sky, and in fact it's right here. You can see there's a whole lot of stuff happening near the galactic center region, but everybody agrees that there are way more GeV photons coming from the galactic center than they expect. So this is a picture here that has the data, from the Fermi Gamma Ray Space Telescope in black, and you can see there's a big bump at around 1 to 2 GeV. And then there are some different models that might be able to explain it. But first, let me talk about what the data is. So first, it's very bright. They don't even talk about sigma anymore because it is so far off the charts. So it's an extremely bright gamma ray source. They can see the spatial morphology of it, and it seems to be roughly spherically symmetric, which is an important point, because that's what you would expect from a dark matter explanation. Now, it could be explained by a couple different things. So in this paper, they looked at 3 different explanations. The black dashed curve is the explanation, that's what you would expect from a model of dark matter with about a mass of 50 GeV, with an annihilation cross-section, approximately that you would expect from the thermal freeze-out process, and with a density distribution that's about what you would expect from standard cold dark matter simulations. That's pretty compelling, and it looks like it fits the data very well. The next thing that looks like it sort of fits the data is millisecond pulsars. And this curve was generated with a particular model of millisecond pulsars based on other millisecond pulsars that have been observed. There's a third thing on here, which is a signal from globular clusters that seems to not fit at all because it doesn't turn over at low energies. So how can we test this thing? We can look more closely at its morphology. So is it really spherically symmetric, or does it exhibit like a bar or a box shape, which you would expect from like the baryonic components, like the regular matter near the galactic center? If it's coming from millisecond pulsars, then we should eventually observe some millisecond pulsars near the galactic center. And we have never seen a millisecond pulsar near the galactic center, so that would be a big new thing. And the other thing that we can look for is if this dark matter explanation is the right one, then that's the dark matter. And everywhere we look, we should see the appropriate signal generated by that type of dark matter, right? So we should see complementary dark matter annihilation signals. This one is still very much up in the air. And that's sort of been, those question marks have been there now for quite a while, but there are new measurements that are coming online. Telescopes are getting more sensitive. Even CTA might help unravel this. So I think there is hope that we will know the answer to this in this in the scale of like a few years. Okay, I want to now focus on nearby dwarf galaxies a little bit. So I showed you this equation before. This is the flux of photons from dark matter annihilation. We measure this, we assume these things, we get a limit on the annihilation cross-section. Many people do this, and in fact, the collaborations that run these experiments, such as the Fermi Gamma Ray Space Telescope, have groups that do this as well, right? And so here's an example of a limit. This is the annihilation cross-section as a function of mass. Everything above these lines is excluded because it would have produced an observable signal in a particular collection of dwarfs. And I also want to point out that the little regions here are what you would expect from the galactic center gamma ray excess. So they're right on the edge of the measurements that are being made from dwarf galaxies. There are some really important assumptions that go into this, though. So one assumption is what the dark matter annihilates to. That's a pretty standard one. We know how to work with it. So in this case, they assume the dark matter annihilates to B quark and anti-quark pair. There's an assumption on the dark matter distribution in the objects that are being looked at. So in whatever collection of dwarfs is being used to make this plot. And then the third assumption is that there is a specific speed dependence of the annihilation. I mentioned before that we often present it as the annihilation cross-section times velocity because that quantity for many models is velocity independent, but that's not necessarily always the case. So when you see a plot like this, it's really fantastic that there's a limit like this. However, you can't then just take that limit and apply it to any other dark matter model. It's really specific to that dark matter model. So after coming up with some interesting and creative dark matter models, my collaborators and I became sort of frustrated that if we wanted to go and use the Fermi data to place a limit on our more inventive dark matter model, there wasn't like a very straightforward way to do that. And there certainly wasn't a straightforward way to do it with current data. So we started by figuring out how to do it with the current data, and then we decided to make it into a tool, which we call the Model Agnostic Dark Halo Analysis Tool, or MADHAT. And the idea here is to, first of all, facilitate comparison of dark matter models with astrophysical data for any kind of weird dark matter models, right? It shouldn't only be standard annihilation to BB bar that gets all the attention. In order to do that, what we wanted to do was an analysis that could be undertaken independent of the dark matter particle physics model. So you can use any dark matter particle physics model and find an appropriate limit, and also independent of the dark matter astrophysics. And by astrophysics here, I mean the distribution of dark matter in these target objects. So to do that, there are sort of three main points that we did. We used an empirical determination of the background distribution. So what photons do you expect coming from that region of the sky? So we didn't have to do any modeling, which other collaborations do. In this first analysis, we used only the number of photon counts in the relevant energy range. So we didn't actually care what the spectrum of the photon spectrum from the annihilation was. And we did a simple stacking analysis, which means that if we had 3 dwarf galaxies, 1, 2, 3, we just count all the photons from them together. So this method allowed a separation of the observational data, the dark matter distribution, and the details of the dark matter microphysics, like what is the particle physics model. And that came out in 2019, and you're welcome to check it out. I put an example here of a model that previously we couldn't, it was really difficult to use the Fermi data to exclude this unless you were an expert in using Fermi tools. And so we were able to exclude this, we were able to look at the sensitivity to this particular model. So let's go into this in a little bit more detail. So if we look at how this actually plays out, because we're looking at a number of different target objects in the sky, right? So we choose a region of interest that's pretty big. 10 degrees is like pretty big on the sky, right? Centered on a target. And then we construct the background probability distribution by sort of randomly sampling around that target region. Obviously, we have to stay away from known point sources, right? There are going to be point sources if you take a 10-degree region on the sky, and so we have to subtract those off. And what you get is a little probability background distribution with a bump. So this is just the number of photons. The red is the distribution that you expect, and the black from this background analysis, and the black line is the measured number of photons coming from that target object. So we can do this with dozens of target objects across the sky. For each object, then, we just count up the photons in the range 1 to 100 GeV, and then we get a number. And you compare that number of the background of the photon count to the probability distribution, and you can place a limit on the number of photons that can be from any non-standard or unknown astrophysics, which would include those from dark matter. And then you can translate that limit into a limit on new physics. For dark matter, if you want to like sort of know how this relationship happens, for dark matter, the number of expected signal photons depends. We often say it depends on the particle physics factor and this dark matter astrophysics factor, and then the exposure, the observation time times the effective area of the detector. And often people say, oh, you can break these up into 3 separate things. And sometimes that's true. So this particle physics factor is part of that flux equation that you might recognize with the sigma v pulled out because it's velocity independent if it is. And then the J factor, we normally think of this as the integral over the velocity or over the dark matter distribution, the dark matter density squared, right? However, these two things can become linked together if there's non-trivial velocity dependence in the annihilation cross-section. And so parts of this, what is actually the annihilation cross-section, can appear in both of these objects. So Mad Hat allows you to handle that consistently. So it gives you the flexibility to choose your target objects. You can even calculate your own dark matter distributions, which we call J factors, and you can specify your own dark matter model. So I already showed you this this is sort of the big picture, like, hooray, we were able to do this thing. On the left, you're looking at the different spectra of photons that you would expect for different dark matter models. These solid ones are the standard 2-body annihilations, but there is a whole range of interesting physics models that have non-standard spectra that previously you really couldn't investigate in a consistent way directly with the Fermi data. Okay, now there were 2 opportunities for improvement. It was like we were leaving information on the table. One piece of information that we were leaving on the table is that we didn't do anything with the energies. We literally just counted the photons between 1 and 100 GeV. But you could definitely bin those, right? And so you can do a binning analysis to increase the sensitivities to spectral features. So in the update, we chose 16 energy bins between 1 GeV and 100 GeV. Similarly, if I have a really big nearby clump of dark matter and a really tiny far away clump of dark matter, which one are my photons going to be more likely to come from, right? Probably the big one that's nearby. And so we can weight the photons based on the likelihood that they have dark matter origin. Okay, I'm not going to go through the details of this, but I do want to say that with Mad Hat version 2, we used 14 years of Fermi-Lat data. We used 54 target objects, and there are actually more than 100 objects that are in our catalog that one could use if they were so inclined. We have energy bins, we do this target weighting, and anyone can put their model in and run a model in 1 to 2 hours and create one of these curves, or you could just check a model point. Is my model that I thought of excluded or not in like a matter of a minute? These are not going to be exceptionally strong bounds, but they are exceptionally flexible bounds. So they're sort of consistent with the level of other bounds using 14 years of Fermi data. Okay, so this is a cool thing. I'm excited about it. I think there are a lot of prospects for future use of Mad Hat in various ways. But there's one thing that I want to point out, which is that dwarf galaxies, one of the reasons that it's important to have a tool like Mad Hat is because we are discovering new dwarf galaxies and new target objects almost like every couple weeks. And in fact, just as we were to post this one, which you can see the archive post date is 2401 with some numbers after it. So we posted this thing just a few weeks ago. And as we were in the final stages, about ready to push go, we're done with the paper, a new dwarf galaxy was discovered. But thankfully, we were able to integrate that into our analysis very quickly. So this is Ursa Major 3. And the uncertainties on the distribution of dark matter are large, but it was a proof of concept that we could just very quickly integrate these new objects. As the Vera Rubin Observatory comes online, it's expected that we're going to have a lot more target objects to explore very quickly. So I think that's a pretty exciting future for indirect dark matter searches. Okay, I want to end by saying a few words about something else that I find very exciting, which is related to astrophysical probes. And this has to do with the formation of stars in the very early universe. How many of you have heard of dark stars? A few people. Okay, cool. So regular stars, what we think of as a regular star is usually for most of its life a fusion powered star, in the sense that nuclear fusion is balancing the pressure of gravity inwards, right? A dark star is an object in which actually dark matter annihilation is balancing the pressure of gravity inwards. This was first proposed by Katie Fries, Paolo Gondolo, and Doug Spoliar in 2008. And it results in some really interesting characteristics for objects that we could observe in the universe around us. So in particular, because of the dark matter annihilation as the power source, that looks very different than a fusion power source. And what you end up with is larger, like more massive, puffier, so like distance larger, colder, much colder than a regular star, and much brighter than a regular star objects. So that's a whole bunch of weird things to put together into one type of object. But that's what you get with this dark star scenario. So let me just go through how those formed, and then I'll tell you one really cool way to detect them. We're talking about here are the very first stars to form in the universe. And if you know about how the elements came to be, most heavy elements were produced actually in stars. So the very first stars didn't have any of those yet. So they were formed from pristine gas, really unaffected by other astrophysical sources. They formed at very high redshift, so in the very early universe. And basically you have this overdensity and the gas starts to gravitate together and it collapses to form a protostar. That's possible when some cooling mechanism allows it to condense. Add in dark matter. Now, in any case, you can define this sort of minimal halo mass in order for this process to happen, for a star to form. First, the protostar forms, then a fusion power star forms. If you consider what the dark matter is doing, the dark matter is also, like as the baryons clump together, because baryons can clump together a little easier, the dark matter actually is going to fall into that gravitational potential well too. And that then you get more dark matter there and more. So eventually, if dark matter annihilates with itself, dark matter heating, the products from that annihilation are going to get stuck in the star and they can be the power source for the star. Whether or not you have dark matter, these first stars are predicted to be very massive, and that has to do with if they can't cool very efficiently, which they couldn't, then you get larger and larger masses because there's a lot of time to accrete more hydrogen and helium gas. Simulations show that the typical mass is more than 100 solar masses. If you add in that dark matter component, the baryons can continue to accrete throughout the dark matter heating phase. And that means you can have very massive stars, like 10 to the 4, 10 to the 5, 10 to the 6 solar masses. However long that dark matter heating phase lasts, you can keep accreting matter. So there are a lot of ways to find evidence of these super weird objects. They're very strange. One really important way is by directly looking for them, right? And we couldn't do that until now, really, because these things formed in the early universe, high redshift more than 10 for those of you who know. Looking for them directly with the James Webb Space Telescope was first proposed in about 2010. JWST launched in 2021 and released its first science results about a year later, including information from the Advanced Deep Extragalactic Survey, or JADES. JWST has hundreds of high redshift objects that could potentially be dark star candidates. However, there are about a dozen that have been spectroscopically confirmed, and of those, only about 3 or 4 are really good candidates to be a potential dark star. But the cool thing is you only really need one. So here are 3 examples. Oh, that's sad. Yeah, this is the only, I'm almost at the end, and this is the only slide that has like a picture where it's really cool to see what's going on. Okay, so this is data from JADES, and it's okay. So you can see there's an object, and it is a spectroscopic survey, so you can actually get the spectrum from each of these objects in a certain wavelength range. And I will show you the middle one. That's okay. If this. Okay, maybe it turned off my laser pointer. So I'll show you the middle one. So this is the flux density as a function of wavelength, and you can see the JWST data is in black here. There's a particular thing that happens, which is that, like, if you're looking for these photons, if they're low enough wavelength or high enough energy, they're going to get absorbed by the by the hydrogen gas around the object. And so you expect that we call these Lyman break galaxies or Lyman break objects, and you basically expect below that Lyman alpha frequency nothing, or below that Lyman alpha wavelength nothing. But then you can see that the rest of this data sort of follow this curve, which is what you would expect from a dark star. Now, do they also fit early galaxy models for what you would expect? And the answer is probably, right? Like, yeah, they're probably early galaxies. So these JADES observations so far for these three objects, they're consistent with early galaxies, but they're also consistent with dark stars. And importantly, there are ways to tell the difference between those two things. So the two main things are to get a better spectral measurement in this wavelength range, which can be done with current instruments, because there are specific spectral features at smaller than 5 micron wavelengths. The other thing is to follow up with the near infrared spectrograph, or near spec, which measures wavelengths larger than 5 microns. And there you expect a divergence of what the spectrum looks like from an early galaxy or a dark star object. So this is super exciting. I think we're talking like 1 to 2 years timeline on this. And it would be really amazing. I mean, one thing that's so exciting is if you see one of these, you have proved the concept that that type of object exists, right? Okay, I have basically talked about WIMPs. I know you're all probably sick of hearing about WIMPs right now. And many of you are probably asking, well, what about all of the other types of dark matter that could be the explanation for these phenomena? There are many explanations that span 80 orders of magnitude, and this is a cartoon, but what we've talked about is basically in this green range, just a tiny area of the possibilities for the parameter space of dark matter. If it's not WIMPs, I would say don't worry. There are lots and lots of other ideas, and there are almost a complementary suite of different types of explorations that are looking to define or to measure the characteristics of these different types of dark matter. So all that is to say that this is a really good time for new detection techniques, which are sprouting up everywhere, to look for different types of dark matter models, and also for paying attention to signals that we might already be able to identify from more interesting types of dark matter models that are not standard. So are we on the cusp of discovering dark matter? I'll let you figure that out, but I remain optimistic, and I think it's a really fun field to work in. Okay, thanks.